Yes, now back to the lecture again. We studied two algorithms up until now, DDPG and TD3, right? The main drawback or the main limitation rather in those algorithms is that we inject noise explicitly, forcefully, right? It doesn't have inherent exploration, right? You're injecting the noise, right? Forcefully rather, okay? Now say assume a scenario where you somehow incentivize exploration like reward maximization, right? What happens in that case? If you incentivize reward maximization as much as you incentivize exploration, what will happen?
Both are not the same sometimes.
Okay. So you mean to say they're contradicting?
Not particularly. They might be at some time and might not.
Okay.
So, but how we merge the two things in one?
Okay.
If the incentive is the same as the final reward, then like we should incentivize the accumulation of the reward more, right? Like not incentivize the exploration at the same time. So we need to reduce the exploration somehow towards the end, right?
Okay, that is one way of seeing it, yes, but you will get a maximum reward only if you explore it enough. You see the point? Like if you do not explore enough, you will not get good rewards. But when you're trying to get a lot of rewards, by exploiting, you will not explore. Right? So there is a kind of trade-off here. Right? No, there is not actually. Because if you explore it enough, right, then you will eventually reach a point where exploration and exploitation, there's no more exploration needed, right? So you will simply exploit.
But this assumes that you covered all the areas.
Yes, that's the exact point. You have to do it. Otherwise, there might be some area in your problem which could contain the maxima, right? And you leave that part unexplored, right? Once you have explored the full environment, there's no more exploration needed, right? So say you have two terms in your reward, okay? Or no, not reward, no. Two terms in your objective, okay? That being reward maximization and exploration maximization, right? This exploration maximization will happen till the point till you don't cover the entire space. Once you cover the entire space, there is no point of exploring, right? You don't get any incentive for exploring at that time. At that time, you will simply have to care or bother about maximizing your reward, right? So SAC is exactly that, soft actor critique.
But I'm trying to imagine in a continuous task, a continuous action covering the whole exploration. For example, you give the example of a drone flying. The number of times it can fly in a specific way to explore is approaching infinity.
Yes.
So, like, how realistically I could explore everything?
Oh, okay. So you mean realistically we cannot have infinite combinations of everything?
Yes, even if going to trajectories.
Yes.
The number of trajectories it can take to explore such an area.
Oh, right. Okay. Yes. That is why that's why you will see in soft actor critique there's a balancing term for that, right? However, the general idea is if you can, you should be able to explore the entire space, right? Okay. Like I told in the earlier classes, RL is pretty interesting in the sense that a lot of results and advancements have happened through empirical advancements, right? And then they got a theory for it, right? Like make some changes, see the result improve, and then try to analyze why that improvement happened and get a proof for it or theory for it, okay? Even in SAC, okay, in RL, what is the general objective? What do you have to do? Oh, at the end, the main goal that you have. No? Maximize reward, right? So you simply have to maximize the expected reward that you're getting. This is the ultimate goal, right? For this, we need an optimal policy. Clear? Now what if I say that this entire objective is modified to ensure that you get maximum reward plus you explore maximum, you increase this thing, right? If you change the objective itself, then you will inherently encourage exploration. You don't at that point have to inject noise into the action, right? And then hope that it will do the exploration. Now here you will reach an optimal, okay, what is an optimal policy? It is basically something that whatever is here, if you are able to maximize it with this, with that policy, then it means, yes, you have an optimal policy. Clear? So in this case, it is only the reward that you are trying to maximize, so your optimal policy will correspond to something that has, that will maximize the cumulated reward that you have. Clear?
Can I ask, in machine learning, I heard the term before called I think double gradient regarding the exploration or the one. From what I understood, sometimes we overfit after a specific training or so, only overfit. So the results get worse in the test, for example. So after some time, they found that some cases, after it can get really low, it can get up again.
Okay.
So I think a double gradient, if I remember, I'm not sure.
Okay.
Called in the data model. But here also, like, if the reward is getting worse, so I'll continue explore, even though the reward is getting worse.
What do you mean if the reward is getting worse?
We're trying to explore.
Yes.
At some time or some area or sequence of action, the
Yes.
reward is continuously going bad.
Okay.
Then I'll continue my path to finish all, or try to get the whole exploration, or we have the both of the goal. Increase the reward.
Okay.
Then do the exploration.
Right.
When doing the exploration at some part or so, I find that my earlier rewards was really high, and now I'm continuously getting bad rewards or lower. What I'll do in this case, I'm trying to think how it will act.
Okay. In that case, you're not doing one after the other. You're not first increasing the reward and then you're doing exploration, or you're not first exploring and then you're increasing the reward. They both happen parallelly, simultaneously. Right? So every episode that you have, the policy or the learning itself happens in a way in which you're not only trying to maximize the reward, but also it is an and there, not or, okay? You are trying to maximize the reward and you're exploring enough, right? You basically are encouraging exploration inherently here. You don't have to inject noise. The actions generated by the actor will itself be in such a way that you will not only bother about, okay, why are we injecting noise there? Because if not, it will simply exploit, right? It will simply follow one path. Why? Because the actor's main objective is to ensure that you get maximum reward. That's it, right? However, in this case, if you inherently put it inside the objective that no, I want a policy which maximizes the reward and which covers the maximum space that you have, which explores enough, right?
Q and B is Q value or other function?
Where is, oh, this is exploration, sorry. Okay, excuse me for my writing, okay. So clear? So if you change the objective itself of RL, you will get SAC, right? Okay, yes, I was telling about this, the intuitive changes, right? RL in a lot, even in the next algorithm that we'll be studying, you will see that they make very small changes. If you look back and you think, oh, why didn't I think of this? I could have done it very easily, especially SAC, okay? When you look at the SAC algorithm, it is nothing but just this one addition term to TD3. You have exactly the same structure as TD3, right? Nothing changes, but the only thing is this exploration term is added. So what they did, they took the noise that you add in the actor and put it in the objective function. That's it, okay? And it is very intuitive. It isn't something that came from a lot of theory, no. In fact, the opposite. For this, they made theory. Got it? Okay. The reason why I keep the title slide and then explain everything and then skip through the slides is because I'm hoping that you people will read the slides later on, and if you have any doubts, you ask me. But I cover everything that are there listed in the slides, right? Clear? Okay. So yes, TD3, DDPG, both are off policy and deterministic. Okay? There are chances because of the poor exploration that they might get stuck in local minima. Clear? And they become sensitive to hyperparameters because of that, maybe. So what we are trying to do here is inherently change the objective of RL such that exploration is incentivized naturally. Okay? Not through reward, not through noise, but because the objective itself now is to explore more. Okay? So basically you want a policy that is maximally rewarding and maximally uncertain. Clear? So we do this through a term called entropy regularization. Okay? And there's a very funny term here, temperature. Okay, I'll talk about it. Okay? So you see, the actual objective is to maximize the expected discounted future rewards that you will, cumulative discounted reward for any policy. However, in SAC, you change that to add this entropy term. Okay? This entropy term is, okay, you know from physics, right, that how does entropy increase, what is entropy? Right, the uncertainty. Okay, why does it increase? How do you change it more? Okay, you have two glasses of water, okay? One is boiling water, the other is normal room temperature water. Which has higher entropy? Why?
Because it changes more or has.
Why? Why does it have more energy? Which energy does it have more? Where does that heat energy come from? The molecules vibrate. Why do the molecules vibrate? Temperature, right? When you heat, when you increase the temperature, the molecules increase in temperature and there is vibration which causes entropy, which is nothing but uncertainty or disturbances. That's why here this term is called the temperature term. Clear? They did not even bother getting or finding new terms. They just took whatever terms were already there and plugged it into RL and made this a very beautiful paradigm of machine learning. Okay. So yes, so here this policy itself will inherently have an objective of increasing the entropy so as to make sure that you explore enough and you don't get deterministic values, right? This is particularly useful in cases where you want to have, where there are slight changes in environment, okay? Like say suppose in a real world platform, okay? Say you are flying an aircraft, okay? A small aircraft for a small distance, okay? The thing that changed, and it is gasoline operated, say there is fuel in it, not battery, okay? So as you fly, right, the weight of the UAV or the airplane decreases, right? But say the decrease is very small, say 5%, the fuel is just 5% of the weight, okay? When you have an RL policy that is trained for a given nominal case, right, in that case, when there is even the slight shift in the parameters of the system that you have, it does not fit well, as in it does not, the effectiveness and the efficiency goes down drastically, right? It's not a linear performance degradation that, okay, fine, for 1% change, the performance will change by this much. No, the change might be more drastic, right? Because it is very deterministic. It knows that at this state, for this system parameters, I need this action, right? So it hasn't explored much. However, with this kind of policies or with this kind of algorithms, the policy that you get is slightly more robust to slight changes in the system environment that you have, the system parameters itself, right? Clear?
About the equation. We discussed about it.
Yes, okay. So yeah, this part is nothing but your actual objective of RL.
Oh, yes, yes.
This part is the term for entropy. Here you have, you're incentivizing the, what do you say? Okay, it is here.
Yeah, what A over S.
Where is A over S? It's A given S. So okay, you have the log probability here. You remember log probability? Okay, what is probability? Okay, what is a policy? In that state, yes, we take it now in terms of log for simplification of calculations, right? And you take a minus sign here. Why minus? Because your log probability will be in, say a probability is between 0 to 1, right? So for any given action, your probability will be 0 point something. So it will have 10 to the power minus 1, right? Or minus 2, or 10 to the power of minus something. So now if you take the log of that, you will get minus of something. So now it will basically be discourage exploration. That's why you have the minus sign there, which is simply to negate the plus, the minus coming from the log probability. And then you add it here. You could simply have it here as well, like minus alpha h.
But can I ask why the log of the probability, how it does, or how it affects the exploration?
Okay, how does it explode? Good question. Okay, so what is this part? The probability of the action, right? So as you, okay, what happens with that is when you reach state S, you will take action A, given a policy, right? So if you do that very deterministically, that probability will always tend to 1, right? You don't want that to happen. You want it to be more stochastic. You want something like, okay, fine, if I'm in this state, I will take an action from this distribution, not just this action. Clear?
So somewhat introducing random actions or random other probabilities?
What do you mean random other probabilities?
You're saying I'll take one different action from this distribution, the probability
Okay.
distribution. So a different action from the distribution. So how it, like, I mean random action the same way we did with epsilon, for example. We choose a random or a different action, different probability of an action.
Okay, no, there you took a completely different action altogether. Here, no, here you basically, instead of giving a fixed value, that term will encourage the agent to give you a distribution of values. And distribution of values are somehow correlated here, you see. Whereas the noise will give you a value here, a value here, a value here, a value here. You see? However, this will encourage the agent to give you an action distribution like this. So every time you poke the actor to give you an action, it will not give you one action. It will be like, okay, fine, this is your continuum. From within this curve, select any action that you want. Right? If you want to deploy it on the hardware, you cannot give it a series of actions to the hardware, right? What you do is at that point, because at that point when you're deploying, the training is already completed, right? So that time you don't want to explore. That time you want a deterministic value. So you simply set the stochasticity of the system to be 0, of the actor to be 0 at the time of deployment, okay? In MATLAB, there's a very elegant way of doing it. You simply set the exploration or I forgot, there's a term, you set that to 0, that's it. So that way you will always get a deterministic value. So even here what it is trying to tell you is, for a given state, take a distribution of action with the action being at the mean, the highest probable action, right? However, you can deviate a little bit, but your overall performance will not change a lot. Right? Remember when we were talking about having a continuous state action value function? Why? Because slight change in action shouldn't change the state drastically. Right? Here, this way, when you get this distribution, right, and say the mass of that aircraft that we were talking about changes a little bit, right? It will then be able to take anything from this action, right? A slight change in state will probably give you this action or this action, right? Got it?
The negative sign here, the negative sign, when we maximizing the objective function, with the negative sign we are reducing the expected value.
Okay. You have this log of pi, right? What is pi? Policy. Probability of taking an action in a given state, right? What are probabilities are numerically confined between this 0 to 1, right? Closed interval of 0 to 1. right? So any probability will be 0 point something, maximum 1.0, right? For maximum value 1.0, log of 1 will be 0, log of 0 will be 1. Anything between that, no, log of 0 will be 0. You don't have log of 0, right? Sorry? You get what? Minus infinity.
It asymptotically goes to approaches minus infinity. Yeah? Goes like that, right?
Okay. So it is 0?
That is undefined.
Yeah, it's not there. You don't have log of
Yeah, log.
natural log, you don't have, but log base 10 you have.
In cross entry in machine learning, log 1 minus y and y might be 1, so it might be log 0.
No, you are calculating natural log, log to the base c. If you take log base 10, you will get a value. I think it's 0.
Yes, 0.
Okay. So, here, okay, yes, okay, any which way. So here this is a deterministic value 0. It means do not take that action in that state. 1 means take just that action in that state. Both of these are deterministic values. So there the log term will be 0. Okay? There the log terms will be 0. So it is, because it is deterministic. However, any value between this will have say 0.3, which is 3 into 10 to the power minus 1. When you take log of this, you will get log 3 minus 1, right? Which will be some value, which will end up you getting a value less than 0, okay? Which will be a negative value. So this minus sign will compensate for this negative value that you get here, and when you plug it in here, it will be plus. So therefore, you are trying to maximize both, right? Clear? Okay. So yes, like we talked about, this prevents premature convergence, so encourage exploration, right? Clear? Okay, this we talked about it already. Yes, okay. So now your action will be a Gaussian distribution, for example, right? With a mean and a standard deviation. So your action will be not a single value but a stochastic distribution. So you select one from that. Got it? Clear? Okay. Okay, yes, there is something called a reparameterization trick here that is followed to compute the gradient, because it is actor critique, right? You need gradients, right? So if you have a distribution, the gradient is difficult to compute, right? So in order to overcome that, you will use something called a parameterization trick, okay, where you will squash the values of the action between -1 to +1 using a tan h activation function. So your actor will go through that, then you will get a range of values which will then help you compute the gradients, okay. So like I said, the exploration is now part of the policy optimization and not an externally added noise. Clear? Okay, and then it follows exactly the same method that we talked about for TD3. There's no difference in that after that point. Clear? You same, again you have two critiques here. The architecture is exactly like TD3. The only thing is the objective itself is changed now. Okay, it goes from optimizing or maximizing the reward to maximizing the reward plus uncertainty. Clear? Yeah, this doesn't change again. Okay, this however, okay. Now you might have seen the term here alpha h, right, which is the exploration term. How will you balance it? Like you talked, right? It will otherwise explore a lot, right? It will give more weightage to exploration than for reward, or the other way around. So how do you do it? If you fix a q value, if you fix this value alpha, then you will face an issue of this, right? However, if you let it be such that it is more dynamic, right? It changes based on the situation, then it is good. So what you do is you basically set an entropy term. You're like, I want this much uncertainty, okay, and you let the training happen, okay. If your, say, your entropy as it goes forward is higher than what you wanted, then you will reduce your alpha. You're like, no, now it is prioritizing exploration way too much. However, if your actual entropy of the system is less than what you have said, you'll be like, no, increase the value of this alpha now so as to encourage exploration more. Clear? Clear? So your algorithm now would be, your action are stochastic, right? They are not deterministic anymore. So you select an action, again you get that tuple that we talked about, S, A, R, S dash, store it in a replay buffer, because again this is also off policy. Clear? You again update your critique obviously just the same way as you do it in TD3, and you do the same thing for your actor, right? However, the only thing now is, when you are updating the actor, your policy or your goal is to not only maximize the reward but also to ensure that you get uncertainty, exploration, right? And you do it exactly like TD3, you will then get a more robust policy. Clear? So it addresses all the shortcomings that were there in the previous algorithms. That's why it is one of the most stable and most preferred algorithms for continuous control applications. Clear? Okay, so here are some things that you can practically take into account. So like I said, if you fix the alpha, you might face an issue, so you simply let it auto-tune, right? You basically let it learn, like, okay fine, adapt based on the entropy of the actual system. Then these are again practical considerations. If your learning rate is too high, your critiques will diverge, right? So you lower the learning rate, that is, take smaller steps basically, right? High variance, change the batch size. Your learning is too small, normalize the rewards, normalize the inputs, normalize the actions as well if you want and if you can, right? And make sure that the coefficients of the weight are correctly allotted, so that way you are getting the objective that you want, and there are no sign issues as well. Like this happens a lot, like say suppose when you are taking velocities or positions as observations, or the errors in position that we talked about earlier, if you're taking that as the input and you do not take care of the sign correctly, like you say you designed a reward function always thinking that you are going towards the goal, right? So that way the agent will then go to the goal and it will keep passing, because then it will be getting more rewards for passing as it moves away from the goal, right? So you have to make sure of this sign as well. So think of this thing when you're designing a reward function. Clear? Yes, okay. If the exploration is not enough, then make the adjustments in the alpha. Yes? From the replay buffer. Batch, you mean, sorry again?
Batch is apart from the batch set. Batch size. By batch size, the batch set of the actor and the critic info.
No, the batch size is the one that we are selecting from the replay buffer. From the replay buffer, it is off policy, right? So what we do is we save that tuple in a replay buffer, and when you take from that batch, from that buffer in mini batches some samples, and you use that to update. Exactly. Right? So yes, that's that. Thank you.